Assalamualaikum. This lecture 7 is the continuation from the lecture 6, which is the same topic, parallel programming approach, but this lecture is focusing on programming shared address based platforms. So let's look at the outline of this lecture. So we are going to learn about thread basics, the POSIX thread API, the synchronization primitives in pthreads, composite synchronization constructs, and the last one is the OpenMP, which is a standard for directive-based parallel programming. Okay, so let's look at the overview of the programming models. Okay, and programming models actually provide support for expressing concurrency and synchronization. So the process-based models assume that all data associated with a process is private by default unless otherwise specified. And then the lightweight process and threads assume that all memory is global. The directive-based programming models extend the threaded model by facilitating creation and synchronization of threads. Okay. Alright, so let's look at the overview of the programming model. A thread is a single stream of control in the flow of a program. So as you can see in the given segment of code, which are two for loop, and then inside the for loop consists of the function call, which is the dot product. Okay, inside the dot product, call another function, which is get row and also get column. So this segment of code actually can be transformed into this one, whereby the function of dot product can be executed inside the thread. So this is an example of the thread program where we call the method create thread, and then inside the create thread, we execute the dot product function. So in this case, one may think of the thread as an instance of a function that returns before the function has finished executing. So we can execute this inside the thread, which is we can execute the concurrent programming. Okay. Alright, so let's look at the thread basics. All memory that being used in the logical machine model of a thread is actually globally accessible to every thread. So the stack corresponding to the function call is generally treated as being local to the thread for liveness reason. And then this implies a logical machine model with both global memory by default and local memory, which is the stack. So it is important to note that such a flat model may result in very poor performance since memory is physically distributed in typical machine. So the memory actually has two models. It's being located in two models, either global or local. Okay. So let's look at the illustration of the local and global memory. So as you can see here in A, so this is the processes that access or the thread that access the global memory. But this kind of model actually has a poor programming practice where it treats stack as a global data. All memory in the logical machine model of a thread is globally accessed to every thread. However, in B, okay, it implement the local memory whereby each of the thread or processes implement a local or call the local memory instead of global memory. Okay, so the logical machine model of a thread based on the programming paradigm. So either it can you want to choose either a global thread or memory, global memory or local memory. Okay, but if we compare these two model, the B or which is the implementation of the local memory is better compared to the global memory. Okay. So advantages of the thread. The first one is when we implement the threads, it provides software portability and then inherent support of latency hiding, so we can hide the latency. And then it's also can be used in scheduling program, and also we also can balance the load when we implement the thread, and it also ease of programming and widespread use. So thread actually easy to use and easy to program, and then is commonly used or widespread use by the programmer. Okay, and then let's look at the POSIX thread API, or POSIX thread API actually is the full name of the pthreads. Okay, POSIX has emerged as the standard threads API. It is a standard model of thread API supported by most vendors. The concepts discussed here are largely independent of the API and can be used for programming with other thread APIs such as anti-threads, Solaris threads, Java threads, and etc. Okay, so this is the thread basic on how we want to create the thread. So as you can see here, this is where how we want to create and terminate the thread. Okay, so this is the term or the keyword that we need to use when we want to create the thread. Okay, pthread underscore create, and then we'll just add a few arguments. Okay, and then okay, we do some function. Okay, join and so on. Okay, so function pthread underscore create, which is this one, invokes the function thread underscore function as a thread. So this one is the thread. Okay, so let's look at the next one. So another example. So this is the example to create the thread. Okay, by using pthread underscore create, we call the arguments. Okay, and then we do some function here. Okay, so as you can see here, uh, another segment of code to run or execute the data. Okay, in this case, the use of ren underscore r, okay, to increase the performance of the thread. And last one, to terminate the thread, we use the pthread underscore exit. Okay. Okay, so programming and performance notes. So note the use of the function ren underscore r in previous code instead of super random number generators such as tren48. Actually, it increased the speed up of the thread. Okay, so the code also can be modified in order to observe of the false sharing. Okay, to observe the thread, either it increase or decrease the speed. So the program also can be used to assess the secondary cache line size. Okay, so this is the performance of the thread if we implement the threads according to the given numbers. So as you can see there at thread 32, okay, 32 here, the runtime of the program is roughly 3.91 times lesser, this one, lesser time than the corresponding time for one thread. If we implement one thread only, actually it needs or required more time compared to 32 threads. Okay, so this one is the example of the execution time of the compute underscore pi function program. All right. So next is one synchronization primitives in pthread. So pthread also can implement the synchronization. Okay, so when multiple threads attempt to manipulate the same data item, the result can often be incoherent. So somebody can confuse. Okay, if proper care is not taken to the synchronization to synchronize them, means if we has no proper scheduling or programming or instruction to handle the thread, so it might confuse the uh, compiler or the processor, and then might produce the false result. Okay, so consider the code here. So let's say if we have this kind of code, if my cost less than best cost, so best cost equals to my cost, which is maybe we want to find the minimum value. So let's say assume there are two threads here. Let's run this code. The initial value of best cost is 100, and the values of my costs are either 50 or 75 at threads 1 and 2. We have two threads here that we run this code with the initial value is 100. So depending on the schedule of the threads, the value of best cost could be either 50 or 75 if we are not consider or not really taking care of the threads. So the minimum value either 50 or 75, whereby if it's actually we give the false result if the value written equals to 75. Okay. All right. So, what is about mutual exclusion? So, mutual exclusion actually is used to avoid the incoherent, to avoid the confusing results during the critical segments execution of the thread. So, the code in the previous example corresponds to a critical segment. So, we need to consider on the thread that uh, will be executed, so we need to implement mutual exclusion. So actually, for example, a segment that must be executed by only one thread at a time. So we need to consider the code, whether the code can be run concurrently or need to wait for another code to be run and so on. So this is called critical segments in pthreads. So we need to implement mutex locks. So mutex locks have two states, either lock and unlock. So at any point of time, only one thread can lock a mutex lock. So if we have more than one lock, so only one lock can implement or apply the lock. So a lock is an atomic operation. So a thread entering a critical segment first tries to get a lock. So it goes ahead when the lock is granted. So if we have more than one lock, so the first one that entry the first thread, sorry, if we have more than one thread, so the first thread that applies or entering the critical segment, it must get a lock. So if the lock is granted to the thread, so it can proceed the program, okay, or the critical segment. So there are several types of mutex locks, or also known as mutual exclusion, either mutex locks, mutex unlock, mutex init. Okay, all right. So this all of this okay has their own functions in handling the mutex locks. Okay, so we can now write our previous incorrect code segment into this kind of code whereby we can implement the lock before we run the control or we run the critical segment. So here, the implementation of mutex locks, then we execute the finding the minimum value. Okay, after the code has been released or have been executed, so the thread can release the lock by using mutex and lock. Okay, so next one, producer and consumer using locks. So the producer consumer scenario imposes the following constraints. So the producer thread must not override the shared buffer when the previous task has not been picked up by a consumer thread. So this is the scenario. So we need to consider this one. It is called as producer consumer when using the lock. So the consumer threads must not pick up tasks until there is something present in the shared data structure. So individual consumer threads should pick up tasks one at a time. So either producer or consumer, it must to make sure whether the task is available to be picked up or need to be right at that time or not. Okay, so to ensure that we need to implement the locks. Okay, so same we can use the mutual locks. So this one is the example of producer before it wants to execute the task. So it needs to apply the lock first, mutex locks. Yeah. And then do some operation or task. And after finish or complete, so it can release the lock by mutex unlock. Okay, so the one is the example of producer. Okay, this one is the example of consumer. So same goes to the consumer when it wants to do something or some task. So it need to apply the lock. So after finish or complete the task, okay, so it may release the lock. So next, so there are several types of mutexes, mutual locks. Okay, so first one, so let's look at the three types of mutexes. The first one is normal, second one is called recursive, and third one is error check. So what is the function of normal mutex lock? So a normal mutex actually deadlocks. Okay, it we it, uh, we're going to have a deadlock situation if a thread that already has a lock tries a second lock on it. Okay, so you need to remember that more than one thread requires lock at the same time. So it will happen a deadlock. So in this case is between the normal mutex. Okay, and then the second one is the recursive mutex. So this recursive mutex allows a single thread to lock a mutex as many times as it wants. So if there is a one thread that's want to apply mutex more than one times, so it may apply recursive mutex. Okay. And the third one is error check mutex. So if the threads implement this mutex, so it will report an error when a thread with a lock tries to lock it again. So as opposed to the deadlock in the first case, which is the normal mutex deadlocks, or granting the lock as in the second case. So if we implement normal mutex or recursive mutex, so it will report the error. Okay, when a thread with a lock tries to lock it again. Okay, so the types of the mutex can be set in the attributes object before it is passed at time of initialization. Right. So overhead of locking. So we already see the lock. There are many types of locks and can be implemented in the threads. So sometimes it might happen the overheads of locking. So locks represent serialization points since critical section must be executed by threads one after the other. So encapsulating large segment of the program within locks can lead to significant performance degradation because of what we cannot run the threads at one time in concurrent or parallel process. So we need to run one by one in serial process. So that's why it lead to significant performance degradation. So we cannot increase the performance of process. So it is often possible to reduce the idling overhead. So when the threads need to wait for another thread, so maybe it will have a idling overhead associated with lock. So same with the lock. So each thread need to implement or apply locks before they want to execute the critical statement. So to wait for the other threads to release the lock, so the other threads will need to wait. So this is called as idling overhead. Okay, so to avoid that, uh, it has one function named pthread underscore mutex try lock. So actually, this lock is typically much faster than pthread mutex locks on typical systems since it does not have to deal with queues associated with locks for multiple threads waiting on the lock. So if you want to increase the performance, instead of waiting for the lock to be released, so the threads can implement pthread mutex try lock, so that is no need to queue waiting for the lock, but it can just execute the critical statement if the threads implementing the mutex try locks. Alright, so this is an example how to alleviating or to reduce the lock overhead. So this is the implementation. So this is the normal application of mutex locks. Do some operation here and then release the lock. So after this segment of code is completed, so then the other thread can apply the mutex locks. So to alleviate or to reduce the idling overhead, so instead of implementing the mutex locks, so the threads can apply the mutex try lock. So it has one status that need to be confirmed, and then it's check lock status equals to busy or not. Then okay, it can do the process. Okay, so as presented here, right? Okay, so condition variables for synchronization. So to implement the synchronization, the threads offers the condition variables to be used. So a condition variables allows a thread to block itself until specified data reach a predefined state. So when the condition variable is implemented, it will allow the thread to block itself. Okay, and then to wait until the specified data is reaches at a predefined state. So a condition variable is associated with this predicate. When the predicate becomes true, so it needs to check whether it's true or false. The condition variable is used to signal one or more threads waiting on the condition. So when it's true, so the threads will be signaled, okay, whether it's ready or not. Okay, and then a single condition variable may be associated with more than one predicate. So a condition variable always has a mutex associated with it. A thread locks this mutex and tests the predicate defined on the shared variable. So if the predicate is not true or false, the thread waits on the condition variable associated with the predicate using the function condition wait. So if the predicate is false, so the threads need to wait. So how we may know whether the thread is can execute the process or need to be waited. So by looking at the function of pthread condition wait. Okay, so there are several condition variables that can be implemented. Condition wait, condition signal, condition broadcast, condition init, and last one is condition destroy. Okay. Alright, so this is an example of implementation of condition variables between producer and consumer. Okay, this one is the declarations and initialization of the condition variables. Okay, right. This is the producer part, the body of the producer. The producer implement the mutex locks. Okay, and then let's do some predicate here, and then it's implement condition wait, signal, and last one is the unlock. Okay, How about the consumer? So consumer also implement or apply the lock, okay, while waiting for the lock to be released. So it has a condition wait, condition signal to the thread, and last one is to release the lock. Okay, what else? So controlling threads and synchronization attributes. So the P thread also has the ability to control the thread and then to make sure the synchronization by using the attributes. So it allows the programmer to change the default attributes of entities using the attributes objects. So an attribute object is a data structure that describes the entity, either thread or mutex or condition variables properties. So once we set all the properties, the attributes can be passed to the method initializing the entity. So this function actually will enhance the modularity, readability, and ease of the modification. So these are the benefits of applying the pthreads API. So what are the attributes objects for the threads? So we can use this one, attribute initialization, to create an attribute object. So some of the object are set date, set guard size, set stack size, set inherit, set policy, and set param. Okay, all right. So these are the attributes object for mutexes, normal, recursive, and error check. Just now that we have discussed before, there are three types of mutex. Okay. And then composite synchronization construct. How to construct the synchronization with more than one model. Okay, so by design, pthreads provide support for a basic set of operation. So higher level constructs can be built using basic synchronization construct. So we can construct the synchronization by using two approach here: read write locks and also the barriers. Okay, read write locks. Okay, so in many applications, a data structure is read frequently but written infrequently. So the data is being read, okay, usually being read by the threads. Okay, but read lock is granted when there are other threads that may already have read lock. So read lock can be granted if the other threads already have the read locks. So if there is a write lock on the data, of if there are queued write locks, so the thread performs a condition wait. So it's quite different with the write lock. If other thread has using the write lock, so the other threads that want implement the write lock, so they need to wait and perform a condition wait. So if there are multiple threads requesting a write lock, so they must perform a condition wait, yes. So they need to wait for the lock to be released first. So with this description, we can design the functions for read lock by using this one, read write lock, R lock. So if we want to use write lock, so we can use rewrite lock underscore write lock, and to release the read write lock, so we can use rewrite lock underscore unlock. Okay, read write locks, the lock data type. Okay, this is the function that we might use to hold the data types of read write locks. Okay, rw lock underscore t. So it will hold the following values: account of the numbers of readers, the writers, the condition variables, either readers proceed or writer proceed or pending writers, and also a mutex, okay, associated with the shared data structure. So these are the example, the implementation of the lock. Okay, so the declaration, and also this is the read lock, and then this is the type just now. okay, holds the values, and then okay, you can see here, okay, the initialization of the mutex, okay, the condition, and so on. Okay, then this is the penny writers just now that we look at the types of lock, okay, like condition read, and last one is the release of the lock. Okay, another example, so the implementation of write lock, okay, and then apply the mutex lock, and then ask the user to pin or wait, okay, for the writers to be released. Okay, and last one is the release or unlock the lock. Okay, this one unlocking the read write lock here, the implementation, and the rest is the implementation of the mutex locks, unlocking, and also the broadcast that we have go through in previous slide. Okay, so the next one is barriers. So as in MPI, a barrier holds a thread until all threads participating in the barrier have reached it. So the functions of barriers is to hold the thread and waiting for the all threads that executed reach the barrier. So barriers can be implemented using counter or a mutex and a condition variables. So to implement the barriers, there are several steps. The first one is a single integer is used to keep track of the number of the threads that have reached the barrier. The second one, if the count is less than the total number of the threads execute a condition wait. So they need to wait for all the threads has been finished. And the last one is the last thread. When the last thread entering the barriers, it will wakes up all the threads using the condition broadcast. Okay. This is the example. Okay. The implementation or the declaration, the mutex, the condition variables, and also the counter. Okay, this is the counter to set equals to 0. Okay, and then initialization of the mutex and then condition wait. Okay, so they need to implement the counter to check whether the thread has been completed or not. So if the barrier is complete, so then it will broadcast and wake up all the threads, okay, to release. And then if the barriers or the threads not complete yet, so they need to perform the condition wait. Okay. So this one is the broadcast function, okay, whereby all the threads has reached the barriers. And this one, the implementation of condition wait, where the threads is not completed yet. Okay. Okay, so the barrier described above is called as a linear barrier. Okay, so the trivial lower bound on execution time of this function is O(n) for n number of threads. So this linear barrier actually can be speed up by using multiple barrier. So use of n divided by 2 condition variable mutex pair to implement for the number of n threads. So this is actually is called as lock barrier. So when we implement the lock barrier, threads are paired up. We pair the threads, and each pair of the threads shares a single condition variable mutex pair. So instead of linear barrier, all the threads are executed alone. So when we use lock, so the threads will be executed in pair. So they need to wait for their pair, okay, to be finished, then they will be moved to the next pair to be executed. So this process repeats up the trees, okay, and then it's also called as lock barrier, and this is the runtime rules as O log P. Okay, so this is the execution time of 1000 sequential and logarithmic barriers. Okay, as you can see here, when we compare between linear barrier and log barrier, So the time taken for linear barrier is quite high compared to the log barrier. So when we implement the log barrier, it will increase the speed up of the process. And linear barrier require more time whereby they need to wait for one another until it finish the process. Okay. Okay. So tips for designing a synchronous program. So we need to ensure this. The first one is never rely on scheduling assumption. So no need to rely on the scheduling. So when we do the data exchange, and never rely on liveness of the data resulting from assumption on scheduling. Okay, no need to consider the liveness of the data, and do not rely on scheduling as a means of synchronization. And last one, where possible, define and use group synchronization and data replication. So all of this actually to increase the speed up and the performance of our parallel process. Okay, so this one, another one is OpenMP. OpenMP is a standard for directive-based parallel programming. So it can be used with Fortran, C, C++ for programming shared address space machines. So if we want to implement shared address space, so we can use the OpenMP. So OpenMP directive provides support for concurrency, synchronization, and data handling, okay, and so on. So it can set the mutexes, condition variable, all that we have learned in the previous slide. Okay. So OpenMP programming model. So usually they implement in C or C++, based on the Pragma compiler directive. Okay. So a directive consists of Pragma OMP, OpenMP directive. Okay. OpenMP programs execute serially until they encounter the parallel directive. So when the programmer wants to implement the parallel, so it needs to use the parallel clause. Okay, so the main thread that encounters the parallel directive becomes the master of this group of the thread. Okay, so another clause. Okay, the OpenMP also can implement the parallelization, degree of concurrency, and also data and link. Okay, the example of the implementation of OpenMP. Okay, and the implementation of pthread inside the OpenMP compiler. Okay, so the pthread here. Okay, OpenMP programming model. Right, so this is an example how they implement the threads. Okay. A reduction clause in OpenMP. So we also can use this one, the reduction, and also the operator that can be specified into the threads. Okay. So the direction actually specifies how multiple local copies of variable at different threads are combined into a single copy at the master when threads exist. So this is the things or the clause that we need to use when we implement the reduction or threads in OpenMP. So example, okay, OpenMP, the number of threads and also the function they want to execute, right? What else? Specifying concurrent tasks. So there are several clauses that need to be implemented, okay? And then this is the example for specifying the concurrent tasks, right? These are the tasks, okay? Random X and random Y. Okay, and then assigning iteration. So we also can assign the iteration by use the clause schedule, for loop, and many more. Static, dynamic, guided, and also the runtime. Okay, so this is an example for assigning the iteration, for loop. Okay, and then another example, three different schedules using the static scheduling class of OpenMP. Okay, three different schedule, so can be implemented. Okay, Okay, parallel for loops. For loops, okay, directive can be used and then being implemented in the parallel process. Okay, so there are several clauses that can be used. Okay, for example, for and no wait. Okay, this is the example of implementation no wait and for. Okay, the section directive to support the non-iterative parallel. Okay, if there is no iterative, so we can implement the section. And then another example, this one, such as declaration of the section, and then it's quite similar to the function here. Okay, then nesting parallel directive. So OpenMP also can implement the nesting parallel, okay, by using OMP nested. Okay, synchronization construct in OpenMP. So also, OpenMP also can implement a synchronization. All right. Okay, OpenMP library. It support number of functions that allow programmer to control the execution, so, such as like this. Okay, get num threads, max thread num process, and many more. And this is the example, okay, the implementation of the function that has been set in the library. Okay, environment variables in OpenMP. Okay, right. Okay, and then last one, explicit threads versus directive-based programming. So we want to look at the advantages of explicit threads and also the advantages of directive-based programming. So directive layered on top of the thread facilitate a variety of thread-related tasks. A programmer is rid of the task of initializing attributes object, setting up arguments to thread, partitioning iteration spaces, and so on. So a programmer has um, take advantage on this one if we implement the OpenMP or directive programming. No need to declare some of the attributes object because it's already written in the library. So there are some drawbacks to using directive as well. However, there are several drawbacks. Okay, and then let's look at the benefits of threads and artifacts of explicit threading is that data exchange is more apparent. So it helps elevating some of the overhead from the data movement or false sharing or contention. So threads also provides a richer API in the form of condition weights, log. Yes, we know that there are different types of logs, condition weights, and increased flexibility for building composite synchronization operation. Okay, we know that there are read light logs and barriers and many more. And finally, since explicit trading is used more widely than OpenMP, tools and support for PTREX programs are easier to find. So for conclusion, so between threads and also directive-based programming that we looked before, which is the OpenMP, the programmers actually preferred to implement threads instead of OpenMP because threads what you use can be right by using many programming language, not only C and C++. Okay, so actually it's easier to find and then more libraries can be obtained when we implement the threads. Okay, so that's all for this lecture. Thank you.